Okay. So, in the previous class we ended with that unbalanced or unsymmetrical fault analysis, right. So, different types of unbalanced fault that occur in a power system is, one is called shunt type fault, another series type of faults. So, shunt faults are of three types, that is single line to ground fault, that is we call LG fault, then line to line fault we call LL fault, and double line to ground fault, that is LLG fault. So, these are the fault very common in transmission system, but it is not like that simultaneously if fault occurs in one phase, say line to ground fault, another two phases line to line fault. This kind of occurrence are very rare, but these three are very common. So, and the example of series type fault is that broken conductor, that is open conductor fault. For example, one phase, suppose one conductor has broken or maybe two conductors broken, but these are very rare faults, but still we will see, we will go for this kind of analysis. So, already we have studied the symmetrical component and positive, negative and zero sequence components, and most important is the zero sequence network for the fault studies, that is more important. So, first what we will do, we will study that your line to ground fault, that is your LG fault. So, for example, suppose that your single line to ground fault. So, suppose this is figure 1, this is figure 1. Suppose at phase A that there is a single line to ground fault, right. Therefore, your in the phase B and C, the bound, that is the boundary condition, right, that is IB will be 0 and IC also will be 0, because because fault, we are assuming that fault has occurred this thing. So, figure this one, it shows a 3 phase generator with neutral grounded through impedance Zn, the neutral is grounded, right, and we are assuming that fault occurs at phase A through impedance Zdf. So, a fault impedance is there. So, it is your Zdf, that means that VA, this VA is equal to actually this your IA into Zdf, and your this thing, that current through phase B and phase C, it is 0, IB is equal to 0, IC is equal to also 0, because fault has occurred here. So, in this case, assuming that we will make some assumption that generator is initially on no load and the boundary conditions of the fault point are that IB is equal to 0, IB is equal to 0 and IC also is equal to 0, because fault has occurred in phase A, and VA is equal to Zdf IA. So, this is the fault current, this IA is going to the fault. So, VA is equal to Zdf into IA. So, the symmetrical component of the fault currents are, we know this from our symmetrical component analysis, we know this, that IA1 is equal to IA2 is equal to IA0 is equal to 1/3 1 beta beta square, 1 beta square beta and 1 1 1. This is IA, IB is equal to 0, IC is equal to 0. Therefore, this IA1 is equal to IA2 is equal to IA0 is equal to 1/3 IA. You will find IA1 also 1/3 IA, IA2 also 1/3 IA and IA0 also 1/3 IA. That means, I1 is equal to IA2 is equal to IA0, all are equal, that is 1/3 of the IA. This is IB0 is you have marked equation 1, IC0 we have marked equation 2, and VA is equal to Zdf into IA we have marked equation 3, and your express, if you express equation 3, that equation 3 that VA is equal to actually VA is equal to VA1 plus VA2 plus VA0. So, VA is equal to Zdf into IA and your is equal to Zdf into IA, but your IA is equal to your 3 IA1, because here we know IA1 is equal to IA2 is equal to IA0 1/3 IA. So, IA is equal to 3 into IA1. So, here we are putting 3 Zdf IA1 here in bracket I am writing IA is equal to 3 IA1. That means, as per equation 4 and 5, then if you come to this equation 4, that all IA1, IA2, IA0 are they are all equal is equal to 1/3. It shows actually it is a series connection of the positive, negative and zero sequence network, because all component positive, negative and zero sequence components are same and they are equal to 1/3 IA. That means an equation and your equation 5 that and this equation 5 VA1 plus VA2 plus VA0, that is 3 ZF into I1. That means this positive, negative and 0 sequence currents are equal, and the sum of the sequence voltages is equal to 3 ZF IA1. So, this equation suggests particularly this one equation 4, right, because all currents, all your sequence currents are equal, right. Therefore, this equation suggests a series connection of sequence network, twice I have written sequence network through an impedance 3 ZF, because it is 3 ZF, this is 3 ZF into IA1. In many practical applications, the positive and negative sequence impedances are found to be equal, that also we have discussed before. If the generator is solidly grounded, then Zn is equal to 0. That means, in your this thing, if your generator is solidly grounded, then this Zn will be 0, and if and for bolted faults, that ZF will be 0. So, that means figure 2 show the equivalent circuit connection. So, how we have made this connection? I mean you will make it like this, that first what we will do, it is a series connection. So, first the black ink I have made it, this is your positive sequence, first you make this is your positive sequence network. So, EA will be there, plus minus, this is Z1 positive sequence impedance and current is I1. Next, that black one, there is other two, there will be no voltage source. So, this is Z2 and this voltage is VA2, and for 0 sequence this is Z0, current is I0 and this is your VA0. Now, as it will be series connection and all IA1, IA2 and IA0 currents are same, right, is equal to 1/3 IA, all currents are same. So, this as a series connection, this is plus, this blue one plus will be connected to the minus. Similarly, here from negative sequence, that from the plus terminal it will be connected to the minus, and finally, from 0 sequence plus will be connected to the minus through 3 ZF, because your VA1 plus VA2 plus VA0 is equal to 3 ZF. So, in this case you can see that this IA1, IA2, IA0 all are same, because this current is flowing like this, flowing like this, flowing like this and flowing like this and returning to that here only, right. So, and this is actually sequence connection for single line to ground fault, and if you apply your what you call that KVL thing, then you will find, I will come to that. So, VA1 plus VA2 plus your VA0, that will be your is equal to your 3 ZF into IA0, because all are same, actually IA1, IA2, IA0 all three are equal, is equal to 1/3 IA. So, in this case, now from this figure we can write that IA1 is equal to, this is the voltage EA divided by your Z1 plus Z2 plus Z0 and plus 3 ZF, because it is a series circuit, it is a series circuit. If I make this one as something like this, if I make this one, it is something like this, it is a series circuit. This is your Z1, this is Z2, this is Z0 and this is say your 3 ZF, right, and this is your voltage EA, this is voltage EA, this is Z1, this is Z2, this is Z0 and this is 3 ZF, and current is here your IA1 is equal to IA2 is equal to IA0. So, that is why as all three are same, we are writing that IA1 is equal to EA upon Z1 plus Z2 plus Z0 plus 3 ZF. So, this is a simple one. So, fault current, your this thing fault current IA then is given by, because this is IA1, this is IA1, therefore, fault current is then given by IA is equal to 3 IA1. So, IA1 is equal to this 3 into then IA1, you substitute here, this is equation 7. Now, under LG fault condition, the voltage of the line B to ground is, now VB is equal to, under line to ground fault, we know this expression beta square VA1 plus beta VA2 plus VA0, we know beta is equal to e to the power j 120 degree, that we have seen also. Therefore, that VA1 from this diagram, from this positive sequence diagram, Z1 IA1, I mean I am just telling from my this thing, from this diagram, Z1 IA1 plus VA1 minus EA is equal to 0. So, I am writing Z1 I1 plus VA1 minus EA is equal to 0 here. That means, VA1 is equal to EA minus Z1 I1. So, here we are substituting VA1 instead of VA1 we are writing beta square into EA minus Z1 IA1. Now, plus beta, now VA2. Now, in the negative sequence you apply again in this network KVL. So, it will be Z2 I2 plus VA2 is equal to 0. So, Z2 IA2 plus VA2 is equal to 0. So, VA2 is equal to minus Z2 IA2, right. Similarly, in the 0 sequence network Z0 I0 plus VA0 is equal to 0, therefore, VA0 will be minus Z0 IA0. So, here I am writing VA0 is equal to minus Z0 IA0. So, here in the expression of VA1 we are substituting EA minus Z1 I1 into beta square, then plus beta into that VA2 is equal to minus Z2 IA2 plus this minus Z0 IA0, or VB is equal to, we can write that IA1 is equal to IA2 is equal to IA0 is equal to IA by 3, we know that. So, it will be EA minus Z1 into IA by 3 plus beta into minus Z2, instead of IA2 we write IA by 3 plus minus Z0 and IA0 is equal to IA by 3. This is equation 8. Now, from this equation 7 we are writing from equation 8 and 7. So, from this equation what you will do, you will this IA is equal to this expression 3 EA upon Z1 plus Z2 plus Z0 plus 3 ZF. This IA you put it here, you put in this equation 8, you put in equation 8 and you please simplify. So, such that I am giving you the final expression. If you simplify, you will get VB is equal to EA into 3 beta square ZF plus Z2 into beta square minus beta plus Z0 beta square minus 1 divided by Z1 plus Z2 plus Z0 plus 3 ZF. This is equation 9. Similarly, if you do in similar fashion for phase voltage your VC, then VC will be beta VA1 plus beta square VA2 plus VA0. Then again same as before, substitute VA1 is equal to EA minus Z1 into IA3, because IA1 is equal to IA3. Similarly, plus beta square minus Z2 into IA2, IA2 is equal to IA by 3 plus in bracket minus Z0 into IA by 3, IA0 is equal to IA by 3. So, equation 10, here also you substitute the expression of IA from your equation 7. If you substitute expression of IA and simplify, then you will get VC is equal to EA into 3 beta ZF plus Z2 into beta minus beta square plus Z0 beta minus 1 divided by Z1 plus Z2 plus Z0 plus 3 ZF. And if fault impedance is 0, then this term will be dropped and this term will be dropped from this equation 11. Similarly, if fault impedance is 0, then your from this equation also this term will be dropped. If ZF is equal to 0, this will be dropped, right. So, that is for the your single line to ground fault. These are the expression. So, similarly, if you now let us consider line to line fault, that is LL fault, right. So, line to line fault. So, suppose in phase B and C we are assuming there is line to line fault. So, figure 3, actually this is figure 3, this is figure 3, it shows a 3 synchronous generator with a fault through an impedance ZF. So, that there is a fault line to line fault through an impedance ZF, when ZF is there. If it is not there, it will be your ZF will be 0. So, between phase B and C, it is assumed that the generator is initially on no load condition. Now, the boundary condition at the fault pointer. So, fault, there is a line to line fault through impedance your ZF, that means IA will be equal to 0. And second thing is that VB, this is ground as reference. So, VB minus VC, this your what you call, we can say this is ZF into IB, but question is that this is IC, this is IB, that means IB plus IC if you is equal to 0, because IC you have taken this direction, IB this direction. At that point that is basically it is going IB flowing this direction, this is this direction. So, opposite direction. So, IB plus IC is equal to 0, and VB minus VC, it will be ZF into IB, because if you apply your KVL like your this way. So, it will be your VB minus VC is equal, that means I mean in this way you put IB into ZF plus VC minus VB is equal to 0. Therefore, VB minus VC is equal to IB into ZF. So, that means IB plus IC is equal to 0, this is another condition, and IA is equal to 0. These are all the we call sometimes boundary condition at the your what you call fault point. So, that means now with this fault condition we will try to find out other things. So, the symmetrical component of the fault currents are, that means we know this IA1, IA2, IA0 is equal to 1/3 1 beta beta square, 1 beta square beta and 1 1 1, this is IA, IB, IC. So, this is actually rewriting this equation from the previous topic, the symmetrical component. Now, IA is equal to 0 and IC is equal to minus IB, these are the boundary condition for your line to line fault through impedance ZF. So, if you put this, we are putting IA is equal to 0, IB will remain as IB and IC is equal to minus IB. So, this is actually minus IB, this is minus IB, from which you will get that IA2 is equal to minus IA1, I mean from this equation another will get IA0 is equal to 0, that means no zero sequence current. So, if you take IA1 here, I have written here that IA1 is equal to from here 1/3 your beta minus beta square IB, and IA2 is equal to from this equation only 1/3 beta square minus beta IB. That means, IA2 is equal to minus 1/3 beta minus beta square is equal to then minus IA1. That is why we are writing from this IA2 is equal to minus IA1 and IA0 is equal to 0. So, there is for line to line fault there is no zero sequence current and when IA2 is equal to minus IA1, I mean it is just in opposition, right. So, we will see later all this. With this, the symmetrical component of the your what you call symmetrical component of the voltages under fault are that VA1, VA2, VA0, we know this, repeating from the symmetrical component only, that 1/3 1 1 1 beta beta square 1 beta square beta 1 VA VB VC. Now, we know VC is equal to from this equation 12, from this 12 VC is equal to VB minus ZF into IB. So, this VB minus VA VB will be there, but this VC is equal to VB minus ZF IB we are substituting in equation 19. So, here it is VB minus ZF into IB, this is equation 20. Now, from equation 20 your what you will get, you make first VA1, I mean VA1, this one VA1, if you make it will be 1/3 of everything. So, cross multiplication I am writing 3 VA1 is equal to VA plus beta square VB minus beta square ZF IB. That means, from this equation your this equation you can write VA1 actually 1/3 into VA plus beta VB plus beta square into VB minus ZF IB. If you simplify and cross multiply by 3 both this side, then actually you will get 3 VA1 is equal to VA plus beta square VB minus beta square ZF into IB. This is actually from this one, just you write one line, I am not writing, understandable, very simple thing. Similarly, 3 VA2, similarly we are making it that this VA2 is equal to 1/3 of this. So, 3 VA2 from this equation will become VA plus beta square VB minus beta into ZF IB. This is equation 222. Now, subtracting equation 22, this one you subtract from this equation, from equation 21 you subtract. If you do so, you will get 3 VA1 3 into VA1 minus VA2 is equal to beta minus beta square into Z dep IB. This is equation 23. If you subtract VA will be cancelled, even beta plus beta square, beta plus beta square VB also will be cancelled. Ultimately, it will remain beta minus beta square Z dep into IB. This is equation 23. Look, we are not doing anything on your what you call on VA 0. The reason is very simple, that initially we have seen that 0 sequence current IA 0 is equal to 0. That means, in that equivalent circuit, the 0 sequence network will not appear for line to line fault, because IA 0 is equal to 0. We will come to that. That means, this beta minus beta square, if you please simplify, beta is equal to the power j 120 degree. So, beta minus beta square, actually it will become j into root 3. So, that means, this beta minus beta square we are putting here j into root 3 into Z dep into IB. So, therefore, from equation 16, right, again I have to just hold on, again I have to go back to equation 16. From this is from equation your 16, right. This one we can write, that 1/3 beta BIB minus beta square IB. That means, from equation 16, this equation 16, IA1 is equal to 1/3 1 into 0, then beta IB minus beta square IB. So, that is why from equation 16 we are writing that IA1 is equal to 1/3, then beta IB minus beta square IB is equal to 1/3 beta minus beta square into IB. So, IA1 is equal to 1/3 and beta minus beta square is equal to j into root 3. I gave you that beta minus beta square is equal to j into root 3. So, here a beta minus beta square is equal to you put here j into root 3. So, IA1 is equal to 1/3 into j root 3 into IB is equal to j by root 3 IB. That means, IB is equal to root 3 upon j IA1, numerator and denominator multiply by j. So, it will be j square minus 1. So, it will be IB is equal to minus j root 3 into IA1. This is equation 25. Now, using equation 24 and your 25, that means, this equation, in this equation, that equation 24, in this equation you put the expression of IB from equation 25. So, in this equation you put IB is equal to minus j root 3 into I1. That is why using equation 24 and 25 we get, if you put in this equation IB is equal to your minus j root 3 IA1, then you will get VA1 minus VA2 is equal to Z dep into IA1. This is equation 26. So, equation 27, your 17 and 26. So, I have to come back to equation 17. This equation 17, that means IA2 is equal to minus IA1, this equation 17. Even 18 also it suggests, because IA0 0 means 0 sequence network will not come up here, because IA0 is equal to 0. So, from equation 17 and from equation 26, right, that means this equation, right, can be represented by connecting the positive and your negative sequence network in opposition, and the equivalent circuit is shown. I will show you. So, from this equation only you have to make you have to judge that how this network will be connected. So, if you do so, look how we can make it, that in this case this is our green color, this is our positive sequence network, this is our negative sequence network, but we know your IA2 is equal to your minus IA1, that means IA1 is equal to minus IA2 other way, IA2 is equal to minus IA1, that means IA1 is equal to minus IA2, that means they are in opposition. That means, this is plus minus VA1 plus minus, it is VA2 negative sequence. So, as they are in opposition, plus will be connected to the plus, right, and similarly minus is connected to the minus, and your from this equation and from this equation if you apply KVL, then you will see VA1 minus VA2 is equal to this condition Z dep into IA1. So, this is your VA1, this is your VA2. You apply now KVL here, then it will be like this, plus your, if you come like this, then plus your VA2, right, then your this current is your what you call, if you take this way IA1, then it will be I1 ZF, that is actually nothing but minus IA2, right, minus VA1 is equal to 0. That means, you will get VA1 minus VA2 is equal to ZF IA1. I mean, if I make it for you, just this thing, if you make it like this, so this is VA2, so it is plus, so it is VA2, right. Then this IA1 current, let us take, suppose this IA1 moving like, of course, IA1 is equal to minus IA2, but we will consider this IA1 only moving like this. So, it is your IA1 ZF and then minus VA1 is equal to 0. That means, VA1 minus VA2 is equal to IA1 ZF. So, that is why this equation VA1 minus VA2, these two suggest actually current direction, that it will be opposition, and zero sequence network will not come, because I have shown you that IA0 is equal to 0. So, this is that your line to line fault, that equivalent circuit connection, positive sequence and negative sequence. Through that impedance of course is there. Now, from figure 4, I mean from this figure you can write IA1 is equal to EA upon Z1 plus Z2 plus ZF. I mean, this direction if you take and apply your KVL like this, then you will get IA1 is equal to EA upon Z1 plus Z2 plus ZF. So, this is equation 27, and fault as it is a line to line fault, at the beginning we have seen that IB is equal to your minus IC, right. IB is equal to your minus IC, it can be made minus J root 3 EA divided by Z1 plus Z2 plus ZF. So, from this this is the expression of, because IA1 is equal to your EA upon Z1 plus Z2 plus ZF, and IB is this one, IB expression is this one minus J root 3 IA1. So, this IA1 you substitute in equation 25, I have not written here, right. So, in this expression, and we know IB is equal to minus IC, that directly I am writing IB is equal to minus IC is equal to, but IB is equal to minus J root 3 into IA1. So, this IA1 you directly substitute, then you will get this I1, then you will get IB is equal to minus IC is equal to minus J root 3 EA divided by Z1 plus Z2 plus ZF. This is equation 28. So, this is actually your line to line fault. Now, next one is that double line to ground fault, that is LLG fault. For example, suppose these two line your first let me tell you, this is figure 5, this is double line to ground fault, we call LLG fault. So, figure 5 shows a double line to ground fault, that is this phase B and phase C, these two are short circuited, then it is your double line to ground fault, and from one fault impedance ZF is here. So, in this case that IA is equal to 0, because it is double line to ground fault, IA is equal to 0. That means, if IA is equal to 0 means IA1 plus IA2 plus IA0 is equal to 0, because IA is equal to IA1 plus IA2 is equal to this thing 0. Then VB is equal to your what you call VC. VB is equal to this total current, this current is IB, this current is IB, this is IC. So, in the fault current is going IB plus IC. I have not written here, but this current is IC, this is IB. So, in this case the current is IB plus IC, this is the current going to the fault, say, during fault. So, that means you can write, and this is your, these two points are short circuited, these two points actually together, just here I have made it separately for your understanding, these two points are short circuited together. That means, VB is equal to your V, then before showing you, then VB will be equal to VC will be equal to your what you call ZF. The idea is something like this, there is 2 points that B and C phases are short circuited, that means your this is your B and C short, this is a common point, right, B and C together short circuited. So, in this case current is coming from your this thing for phase BI, and from C it is your IC, IB and IC, and this is your what you call, this is your fault impedance ZF, right, and this is ground, So, current here current actually going through this is IB plus IC, as these two points are common. So, VB and VC both are same, this is VB, these 2 points are common is equal to VC. Therefore, VB is equal to VC is equal to ZF into IB plus IC, because these 2 points are common. So, in that case, I hope this simple thing I hope you have understood. So, in that case we can say that VB is equal to VC is equal to IB plus IC into ZF is equal to 3 ZF into IA 0. This is equation 31. Thank you, again we will be back.